In addition to Jay, Tom, and Mark, we have Abram, Zoe, Dave Armstrong, and Neil, I think. So we have the TPC, so I want to thank them again for working with the authors and putting together presentations in the first KGx event. So maybe one thing I'll ask the TPC now that we've done this, is there, what's your number one pick area that we really have to know is good to build and yield systems? I mean, because as we said, we want to expand from known good die to having product that is good and with all the right yields and costs. Is there one area that X really has to be known good? Zoe, can I get you to go first?
Yeah, yes, definitely. I think it definitely starts with wafer sort, getting the highest coverage that you can. And that starts with EDA vendors providing good data sets, particularly like scan, at-speed scan, memory BIST, fully programmable memory BIST, SerDes, testability. So definitely wafer, you want to get as much out as possible at that area and even characterize over temperature as much as possible. And I think, going back to what Mark presented, combining what Mark presented with what Jay presented at the end could be quite powerful. Yeah, because then you may potentially would have sensors to measure where defects are occurring, and how would you combine those two to be super smart, and those things that you can definitely use at wafer sort.
Okay. And Abram, you want to chime in?
Absolutely. I mean, definitely wafer sort to start with. I think in this kind of disaggregated chiplet world, we also need to recognize the impact of the interconnect and the fact that all of the interconnects are, in these type of products, are buried. So how do we, and maybe a solution for this also is sensors and specifications across interfaces. So how do we not only ensure that the die themselves are good, but also the die-to-die interfaces and the ensembles are also good. So kind of taking it maybe one step up into the package level, where you'll have thermal crosstalk, electrical crosstalk, noise issues that are hard to capture at the die level. And how do you now guarantee that the ensemble is now good? I think that's a really big upcoming challenge, especially for products that have dozens, if not hundreds, of chiplets in them.
Okay. Dave?
I was struck that pretty much everybody talked about outliers. And it occurred to me when you're saying what's known good, I think we need a known good baseline. Otherwise, we don't have outliers for any of this stuff. And that's harder to do than I think a lot of us might think. Because there's trends, there's long-term trends, there's short-term trends, there's eyes looking at things, whether it's optical inspection, and in Jay's case, in some cases, some people, some tools, whatever. So to me, no good baseline.
Okay. Okay. And Neil?
Sure. What was, I think, similar to Dave's comment, right? And some of the stuff that was presented with things like digital twins, right? If we can kind of establish this baseline of what we expect, right? How does that feed back into our test and other capabilities, right? It basically leads back to smarter test limits, right? Looking at more complex limits, results of lots of different tests versus single test binning, right? All these kind of things just lead to, if we can use more design EDA data, build up models of our device, use our libraries from the fab, build all that into kind of this somewhat predictive model, and use existing data from other products into new data, using some techniques of machine learning, of transfer learning, right? Old products to new products, you know, that is likely to bring us to, you know, a better way to catch these outliers and look for things that are going to be hidden that we wouldn't traditionally find. So.
Right. And you know, as I asked Jay, I think we always need to do it both ways. You find something with one tool or one method process, why didn't you find it with the other tool, or you know, the reverse? You know, it's because if there's something there and it is a short, for example, electrically that you can see, it's like, why didn't it show up in the test results? You know, for example, and things like that. I'm going to ask a few more questions, but I also will let the audience put things in the Q&A tool. And actually, I'm going to try this because I see there are a few people with their hands up, including Phil Nye. So I'm going to, we'll let Phil ask a question because I'm sure it will be good. Everybody can duck, but let me give this a try and see if I can get this to work. Hold on. Back here, allow to talk. Okay, Phil, you want to chime in for something?
If I raised my hand, I did it by accident. I was probably just playing with buttons.
Well, you're known to break a lot of things, Phil. So
yeah,
welcome.
But this was really good, Iris. Thanks for setting this up. So if I'll just came up with a question. Jay, let's say you're doing a reasonably high volume part. I don't know, some GPU, let's say.
Yes.
Are you proposing inspect all the wafers, subset? You know, what would you propose for? At least.
So I think you're asking exactly the right question. If you said I want to implement IPAT for my whole fab for my entire WIP, it's a lot to bite off. But if you said I'm making multiple devices and I have this customer who particularly cares about known good die or a particular quality issue that needs to be resolved, well then IPAT's a great solution. And actually with the high-speed inspectors that we're using for the bigger design rules, those systems look at more than 100 wafers an hour. And for the cutting edge design rules, it's more like 40 wafers an hour. So one inspector can cover 10,000 wafer starts of WIP per month on between 2 to 4 layers. So actually it's not terrible as long as you aren't trying to do 100,000 wafer starts a month on every device on every layer. It's manageable economically.
Okay, thanks.
And Jay, like we have, you know, well, some people have test flows that skip die that are defective, you know, or you have other data, so you skip the die before even testing it, either because you detected something earlier. But with the visual scanning, does it have to do the whole die of the whole wafer, or could it just do particular areas? Let's say you knew there was a massive defect 2 layers down. Would you still inspect that layer, all the subsequent, that area of the wafer, all the subsequent layers?
So the movement of the wafer into the optics is the trivial part of the whole thing. So there's no benefit to skipping around. The whole wafer will always move under the optics. So, you know, at 100 wafers an hour, there's no skipping around. It's going to scan the whole thing.
Got it.
Okay.
Okay, cool. Okay.
So sorry, let me ask a follow-up then. Jay, if you were recommending to somebody doing this, would you say don't test some specific dies, or test it but don't ship it, but let's keep doing the correlation analysis?
Well, I think it's a maturity curve. I think you would definitely have to prove to yourself that it was correlated first. There are folks who are, there was one customer who has told us about a use case where they have very mature process, lots of very, very small die, and wafer probe takes them hours. The probe is correlated to how many die are on the wafer, whereas the inspector doesn't care how many die are on the wafer. It's going to do it in less than a minute. So if I can prove to myself that IPAT scores are correlated to probe scores, well, maybe I'll just ink some of those things off based on IPAT. I'll package the rest and let final test sort it out and skip that probe. That's not everybody, but that's, you know, a particular small die use case.
Okay, thanks.
Sure.
Thank you. Thank you, Phil.
Can I follow up on that just slightly?
Sure.
This is Dave. So following up on my thought of outliers being the metric, I mean, is your metric there, Jay, that you don't need any more tests and that, you know, the whole wafer is now green because you've made enough progress with it? Is that what was happening there? I'm trying to figure out what happens with automotive customers specifically as we go for higher and higher DPM, better and better DPM. Does the orange dots become red and the green dots become orange?
Well, no, I think you asked a good question about known good die in particular, but it varies. It varies by use case, by mission profile, by environment for that particular die. So that was the whole thing. I, as the guy running the inspection, may not know all that information. So somebody smarter than the guy setting up the recipe needs to know where those limits need to be for this particular die, this application, to determine whether a die is green, orange, or red. Very application focused, I think. But you're right. I think at parts per billion, the question is, where are those thresholds? And typically the data I've seen tends to point to it. There's usually some sort of shoulder. These are clearly the outliers. And then the next part is a little fuzzier. Is it green?
What
Is
if
it
a good
orange?
die during final test becomes a bad die in electrical test later on in the supply?
Sorry, it's a question for me, Tom. I didn't understand.
Yeah, what if a good die in the final test becomes a bad die as a result of soldering, packaging, and, you know, or whatever operations you do on it downstream?
Yeah, so I guess the question is, you know, was there a latent defect that got activated somehow through burn-in? Is there a packaging problem? Is there a handling problem? There's lots of different sources there. So I think this goes back to the traceability that you're pointing out and that Mark was pointing out. What can we learn about where this die's been, how it's been handled, what path it's been through? Not only that, is it traceable? Is it actionable? Is it timely? Can I, you know, recognize something at packaging and make the fab see benefit from it?
Or do we need to somehow add together all the outliers from all the steps, including the final steps, and then bring it all back somehow or another and figure out what really caused this problem in the first place?
There we go. Go ahead, Ann.
Okay. Lots of good presentations, information out there. In the issue of known good die, right? We're putting die either stacking on top or we're putting it on an interposer. I didn't hear anybody address, well, how do you make sure the interposer, which is doing some of the interconnect, how is that being tested or inspected? In addition, right, when you start, this is kind of more on the inspection side. From all the writing and research I've been doing over the last couple of years, I've become convinced there's a lot of value in 100% package inspection because of those bumps and because of, especially when you go to hybrid compression, which I'm surmising is going when you're using that in the heterogeneous area, though I'm not 100% sure. So 2 questions. One, what are we doing to make sure the interposer that's connecting these 5, 50, or 100 die, you know, together? And 2, what is being done to check the bumps before you do that? Because electrically, you can't always find those. And while it's great that Proteinics can help me find, you know, things that are gradually failing, I want to avoid some of those up front.
So you just put the perfect breadcrumbs for the next KGx event, because this one's focused on wafer and we were going to move upstream to the packaging, but it's still a great topic. So if somebody wants to, on the panel, want to make some comments about, you know, package and package inspection and package test, please do so.
So I'll take the first bit, and then probably on the inspection, I think Jay will probably jump in. So in terms of the health at T0, so things like a bunch of bumps weren't connected or on your power supply grid, we can actually detect those use cases and create alerts around it. So you can start to find those trends, not only on like critical paths for die-to-die interfaces, but other effects. So it could, we could look for things like schmutz in a socket where, there's a difference in SLT versus final test, but we could also find things as you're creating these really complex multi-die packages and sort of say, is there patterns in terms of, how many power bumps are connected or ground bumps? And then that could lead to a process improvement. It could also lead to maybe a programming of what the voltage supply should be. So that way you help overcome some of those problems and get more yielded modules. So there's lots of ways that you can use the data now that you have the visibility. And that's why I was talking about, using the chip as an environment sensor for the rest of the system as part of my talk. If another panelist wants to jump in.
Okay, Jay, did you want to talk about bump inspection or?
Just that those types of systems exist, both for bump size and coplanarity and all of those issues. So yeah, there are systems that inspect the components themselves, the interposers, IC substrates, all of that stuff is, you're right, it needs to be run under control, and the industry's responding, including KLA.
Yeah, okay.
And I would
So
also
now,
comment that active interposers are just now, in my opinion, starting to be designed. And certainly people are looking at testing active interposers as they would a die.
great. So now I want to just shift this conversation to data. All three of you talked about massive, massive, massive amounts of data, being generated, being processed, being secured, being transferred. I mean, wafer sort, years ago, some people didn't fully data log test because they couldn't deal with the data. Wafer sort now probably generates huge amounts of data, but I think you guys are talking about orders of magnitude more data. Are we even going to be able to keep up with this? I mean, what do we need to be thinking about in terms of data and the challenges the data presents? I mean, one of the questions I've got is, okay, you've got a product with a 10-year or 15-year service life. Do you keep your manufacturing data for the last 10 years just so you can process an RMA maybe? Or, what are the issues? I mean, let you guys jump in there. And Neil, I know you deal with this every day, so please enlighten us.
I mean, the short answer is today storage is cheap, right? So yes, you would keep that data for 10 years for sure. As long as you're going to need it, especially with cloud services and cloud storage, right? Our storage is cheap. It's never getting cheaper. So, by making use of these, cloud service offerings, there's no reason not to collect and store as much data as possible. Yeah, technically there's challenges in moving it. But those are kind of all solved. We talk about lots of data. We're pretty small if you think of Netflix, YouTube, and so fortunately they've pioneered this and solved all those technical problems for us, right? What I think our real challenge is that's a bit different and unique to kind of our industry is finding the proverbial needle in the haystack, right? Is we're trying to get something like a customer return and correlate it back to an issue. And you might have hundreds of millions of data points that you're trying to correlate to, and you don't know which one is the one that had an effect, right? It's just if someone could solve that, it would be the holy grail of semiconductor manufacturing, right? If I could just plug in a unit and it tell me what caused it, we could skyrocket yields and make lots more money, and somebody would be really rich. But I think that's the number one problem is you can have hundreds of analysts looking at the data for months and months at a time and still not maybe find it. And the issue, and it's we might not even have the data, right? That's the other piece. Like we might not have, as you talk about package inspection steps, right? Is that a common place that people actually take data and keep it, right? Are manufacturers providing that to us, right? So it's just this ever increasing problem of we need more of it, and we need better and smarter ways to analyze it and kind of sift through it to get to an answer, right?
Well, I would throw in that the storage of the data is cheap, but as you want to do more and more machine learning or correlation, that's where it gets expensive. And as your data grows, if you want to just keep doing this analysis over 10-year-old data, I think the costs are just going to be prohibitive. But I mean,
yeah, for sure. The compute you bring to is expensive, right? So you've got to be smart about what you're going to compute, right? But if you're talking about like an RMA 9 years down the road, right? There's efficient ways to get at your 9-year-old data. And you would only operate on that small chunk of the data that you care about. But that's kind of, again, the same problem is you have so much of it, you got to efficiently sift through it, right? And so all these AI machine learning techniques all come into play, right? And you've got to apply your knowledge from every product and every process node and every step to every new product and process node and step, right? Because you don't want to repeat the same mistakes and analysis you've already done, right?
I'll swim against the stream just a little bit here because we produce petabytes of noisy data per day, and finding a correlation is easy. Finding the cause is hard. So definitely can't get rid of that expert knowledge in the stream somewhere to recognize what matters.
And that is why AI techniques based on data alone are not as effective compared to AI techniques like you described, Jay, where it starts from the experience. You train it based on the experience because that limits all the noise that a pure algorithm will not be able to detect that easily, right?
And that's kind of why we're deploying those algorithms into people's systems, looking for particular features. And I think the velocity of data once you get into the field gets a lot lower. So you don't have to send it back, and the test techniques don't map. Like the nice thing about what we do is you can apply that same technique at the different stages, but for the most part, you can't take those measurements that you would have taken at tests. So getting those correlations is difficult. So there's lots of great challenges with the data itself.
And Tom, go ahead.
I was just noticing, Niels was talking about saving RMA or getting RMA data from 9 years ago, which to me made sense. I want to train based on as much data as I can for as long as I can. But Jay threw a monkey wrench in that. if you're getting a petabyte a day, 9 years worth of data is certainly not realistic. So what is a reasonable time frame that I need to be saving data for a training?
I think those are two different use cases, right? Like there's having your data if you want to take a customer return and kind of root cause and do some basic analysis on, right? Then you want to be able to get to it. If you're doing training, I don't think there's any clean answer, right? It's what you can afford to do, I guess, is kind of where you get to, right? And it's a lot of it's getting better at the techniques, right? There's a lot of things like transfer learning and all these other kind of techniques in the area where you don't have to go back to your massive data set to retrain, right? You can also measure all your model drift and all these other things, right? Did your underlying assumptions for that model change or not, right? If they haven't changed, do I really need to go retrain that model? I may not, right? So unfortunately, I don't think there's I can't say, hey, keep your data for 2 years. I can say save your training data set, right? You don't really ever train on your entire data set, right? Because then you get overfitting and all these other problems, right? So you're going to create a very specialized training data set. And yes, I would keep that training data set around for a model in case I ever needed to revisit it. But that's going to be a much smaller portion of my data than, say, saving all my manufacturing data for every unit just in case, we do need to come back and look at something, or we need to prove, something existed for a customer, right?
So we'll need to shift the conversation from the cost of test to the cost of test data, or something like that, or managing and storing and analyzing and things like that. Let's do one more question, and I think Jay, you not Jay, sorry, Tom, you talked about bad actors. How do we check and believe the data we're given? And there are certainly ways of validating it and, encrypting and blockchain and all that. But, how do we really, know that the data is good and it's not just data that was copied from another batch? Somebody said they ran the test and they just replayed the previous test data or something like that. You're on mute, sorry. Tom.
Before I answer this, I just want to say I'm probably the only guy who cares about bad dyes. Because I want to make sure I collect those that they don't go to the wrong hands, because they go to the wrong hands, you can very easily take a picture of it, reverse engineer, and then come up with a lot of counterfeits. So there is an important motivation to also care about bad guys. Now, with regard to the data, I will use the example that the gentleman brought, which is a manufacturing quality assurance, right? And you can look at it from a metrology point of view, the steps that you take, or you can look at it from a testing point of view. But I will use the simple example of an enterprise, because there are known standards in the industry like 2243 or IEC 62443 that says I'm a trusted supplier. And people build ecosystems about that, but then a rogue engineer goes in there and an incident occurs and gets popped up and everybody in the community knows. There's no known solution today to worry about rogue actors. The concept of digitalization, what it says is that in every enterprise, you have an LDAP where everybody's registered, and you have processes whereby you know who did what when, and you can add the concept of timestamps. That is also very appropriate in manufacturing. So if you know that certain tasks take certain time, and they have a begin timestamp and an end timestamp, that's part of the digitalization, all right? You also know who was the operator that was basically in between those two timestamps. So if you know that this test operation would take, let's say, 2 seconds, and it takes 4 seconds, immediately you have to go dive into analytics and say, gee, was that because the machine went down? Was that because the operator did something and stopped it? And now you get into the business of enterprise data that you don't necessarily make available outside, but you use it to understand who worked on what part, what version, when, for the purpose of being able to trace how this data is generated. That's one. The second thing is that you can put mechanisms in any process for a process step for the data in and the data out to be encrypted and decrypted as part of the operation, and then can become available with the key. So blockchaining on one hand can help you prevent anti-tampering, because you will have many people voting and saying, I know what it went through. But the business of digitalizing and encrypting the data in and data out and making it available with a key downstream is absolutely necessary. And I think that as we move to more connected devices, this will become very important. Today, in the commercial world, people don't see that as a risk. The DoD world sees that as a huge risk because of the pipelines and the infrastructure, states, national accounts, etc. And it is very likely that this will start from DoD, the digitalization process, for backtracking all the people that worked on the project and what they did exactly. And that's underlying infrastructure. It's a lot of work, but it is actually, once you do it right, and you put the process steps right for 3 or 4 steps, it is very scalable, because the only thing that changes is the data sets that go in the inputs and the outputs. That's the idea.
So in the first example, the timestamps, you're looking for outliers. What took longer, or what took a different flow than what you were expecting, and then you dig into those kind of outliers. And then the second one is to have a record of the custody. Okay. So, but I think we've made progress as an industry, like say external markings on devices, but it sounds like what you're talking about, you're going to need to be electrically able to connect to the device to really identify what it is.
We're talking, the progress we made is provenance of assets,
Right.
right? So you can identify, you can authenticate, you can test it, whatever. We're talking about provenance of workflow process. And that applies to EDA and manufacturing. I had an engineer who did the synthesis, the place and route, the verification. Now, in any place there where you don't verify, but you modify a netlist or you modify the function, there's an opportunity to inject a Trojan, all right? So you need to know, the engineer invoked a tool, you know, what was the source code there, or what parameters he used, and all that stuff. So that's part of the digitalization. It's metadata that you keep around to be able to trace back what was done in the process of design or in the process of manufacturing and assembly, all right? In the case of manufacturing and assembly, you add also the timestamps because certain operations, the batch operations, take a very predictable amount of time. And the only way you would deviate from that is because either there was a machine down or there was a problem or the operator brought it down. If they brought it down, then what did they do? Because it could be a wafer, they could have taken something in there and basically take a picture. And once you have a picture, you can go to reverse engineer and create counterfeits right away. All right. So those are, the other word to use it is instrumentation instead of digitalization. All right. You instrument your workflow processes. More data.
Right, more data.
More storage.
So I think we all have to sharpen our data management skills and figure out, and you know, there was a few questions related to AI machine learning. I think there's going to be much more of that in our futures. We're seeing the beginning of that, but I'd like to thank everybody, the presenters and the committees for the committee for putting together a great event. And I want to thank everyone. I want to thank everybody once again and wish everybody a good rest of their day. So thank you, everyone.